In this video, we're going to go through a number of examples of looking at carbocations and discerning whether or not they will rearrange. So our objective here is to treat these as like the initial carbocation that we would have formed in a reaction. And we'll say if it's going to undergo 1,2-hydride or 1,2-methyl shift, or we'll indicate if it doesn't rearrange. Looking at the first example here, the carbocation is initially secondary alkyl. I see this adjacent position happens to be more substituted. And in this case, we could have a 1,2-hydride shift and relocate the positive charge to the tertiary alkyl position because that's more stable than the original secondary alkyl. Rearrangement would be spontaneous and would happen favorably. This will be a 1,2-hydride shift. Rearrangement led to added stability. In the next example, carbocation is initially secondary alkyl. Now the adjacent position is more substituted. There's no hydrogen there, but there is a methyl group. Therefore, we will have a 1,2-methyl shift. Methyl group shifts over to where the carbocation was. The positive charge is now at the carbon from which the methyl shifted. Now pausing, notice we have here, as a result of that rearrangement, we formed a chiral carbon. When that methyl group shifts over, if I'm creating a chiral carbon, that methyl group can shift from above or below the plane, which is creating different stereochemical situations and structures. Now that could also happen potentially with hydride shifts as well. Looking back at the very first example, when we shifted over the hydride, we didn't generate a chiral carbon, but that H could have shifted from above or below the plane. It's just not relevant because it didn't generate a chiral carbon. But when we did this methyl shift, we did generate a chiral carbon, and therefore we should acknowledge that that could have shifted from below or above the plane. In the next example, the carbocation is initially tertiary alkyl. And when I look at the adjacent positions, those are both tertiary alkyl. So there's actually no more stable position to move that positive to. In this case, there is no rearrangement. There is no more stable structure to be achieved. In this next example, we're starting off as tertiary alkyl, and I see that the adjacent position is tertiary and benzylic. So what I could do here is do a 1,2-hydride shift. And as a result of that 1,2-hydride shift, the positive charge is now located at the tertiary benzylic position, which is more stable than the tertiary alkyl. So here we have a 1,2-hydride shift. We've gone from tertiary alkyl to tertiary benzylic, achieving more stability. And notice that as we've shifted over the hydride, we did generate a chiral carbon. Therefore, that hydride could have shifted from below the plane or from above the plane. All right, 1,2-hydride shift. The next example is kind of funky visually. Notice that the carbocation is initially primary alkyl, and the adjacent position is quaternary and benzylic. If I were to shift over the methyl group here, I could have a rearrangement that would lead to more stability. All right, tracking with you. We're shifting the methyl group to this carbon here. So this was where the carbocation was to begin with, and we've shifted this methyl group over. The result is the positive charge is now here, and that would be tertiary benzylic. Tertiary benzylic. 1,2-methyl shift. In the next example, we're starting off as secondary alkyl instability. I have a primary alkyl to the left and a secondary alkyl to the right. Those positions would not be more stabilizing to the carbocation, therefore, no rearrangement would be observed. And finally, in the last example, the carbocation is initially secondary alkyl, and I'm seeing that the adjacent position here is secondary benzylic. Now, there's no methyl group, there is a hydrogen, and if there's a hydrogen, it will be a hydride shift. So I'm going to shift over the hydrogen, and as a result of that, the positive charge is now at the secondary benzylic position. All right, so a big takeaway from this exercise is if rearrangement can occur, it will occur, and it will occur if we can get a new carbocation that is more stable than the original. If there's a hydrogen at the carbon that we intend to rearrange to, it will be a hydride shift. If there's no hydrogen, but there's a methyl group, it will be a methyl shift. And if we do our hydride or methyl shift, and we're creating a chiral carbon as a result of that shift, the group that's shifting over can actually shift from above the plane and below the plane, stereochemically speaking.